Welcome back. This is Xfixium, and welcome to the How to Make a Master System Game Using Devkit SMS tutorial series number 12. In this tutorial, we go over the actual player source logic, we go over the details of streaming tile data to the VDP, we create logic for animating the player graphics, we also go over what player states are and processing those states. This is a big one. Let's get into it. Okay, we're going to be putting together our player source code, and the first thing we're going to do here in the beginning is define our constants for the player data, and I'm going to go and show you some information about that. So we go into SMS Tile Studio, and what I'm going to do is create a new meta sprite here. And I'm going to import the graphics for the meta sprite to our resources, and we're going to go to sprites here, and we're going to choose our main import sprites. What I'm going to do is do this in a different fashion. Before we put this in tall mode, which means 8 pixels wide by 16 pixels high, and we went and just grabbed the entirety of the sheet and I added it that way, and that's the reason why I did that, is just to export the sheet itself, not any other sprite data or anything of that nature. So, but here we're going to do a little bit different. I'm going to create the actual animation just for the animation going right for Miss Pac-Man, or going the direction of to the right. So I'm gonna grab this one first. I'm gonna add it. And then the second one, add. Third one, add. And then it goes back to this one. I'm going to add that. So hit OK. And then here we can see Miss Pac-Man. And if we go frame by frame, we can see the animation that Miss Pac-Man has. And we're typically in a standard way of doing the graphics. You would load all your animations into VRAM ahead of time, and then you just point to a different tile ID to update that animation. But since we are streaming player 1 and player 2, it's a little different, and that's why we took the approach of exporting the entirety of the player sheet here. And what we do is, instead of doing it in that way where we load all the frames, which is way too many, because here if we load all this information to VRAM, there wouldn't be hardly anything left to do. Or even if we just put in player 1, it would be too much in VRAM. As you remember, we have about 256 tiles to play with, and a lot of that's going towards the ghosts. So the ghosts will be done in that manner, but as we talked before, the player 1 and player 2 will be actually streamed into these 4 tiles here. So taking about 8 tiles worth of data for player 1 and player 2. But I just wanted to show how we would, or how we could be exporting this from here, or how that data looks like. So we want to create this data for Devkit SMS, and there's an export option here that we can do. That's called export for Devkit SMS to clipboard. And typically what that would do is create all the information that we need for this particular animation and for this particular sprite, if it was traditionally set up in VRAM. And we'll be doing that more with the ghosts, and you'll see that, but I kind of want to go over, this is going to be a quick preview of some of that information. So from there, I'm going to hit Control V, and what Devkit SMS does for us is it'll take the name of the sprites that we created, which here I didn't really give a name. I would typically put, player 1 or something like that. What it does is it will create the durations between each frame. So each frame has a certain amount of time that it displays before it moves on to the next one, and we can define that here within SMS Tile Studio using this. But in this case, we're not, the sprites and the frames and all that sort of thing is actually very simple here. There's not a lot of different things that Ms. Pac-Man does graphically, so it kind of makes no sense to have this. It would be for each frame, so each duration would be about 10 frames here. This is what we're saying before it moves to the next one, because here when I created it, it had 4 frames, so 0, 1, 2, 3, so that's 4 total frames, and here we have 4 durations that would apply to those frames. So here we're saying, okay, each frame is, it lasts for, I mean, each animation frame, the duration of showing it on the screen is 10 frames. So that's what this means. But we're not going to use that, so we can totally discard that. And here we can see what the actual Metasprite definition would be for Devkit SMS. Devkit SMS has a whole bunch of other functions outside of the Metasprite functionality. It has things that where you can add the sprites one by one, or you can add sprites in succession. So you can add 2 sprites together, or you can add 3 sprites together. It gives you that other flexibility there if you want to do it that way. But here we're going to use the newer functionality with it, which is called its Metasprite functionality, where you just define a group of variables in succession that makes up your sprite. So here we need to focus on these 3 numbers here. So the first number for this definition is the X offset. So this would be the horizontal offset from whatever your origin point may be for the sprite, but this also can be defined just as straight up, it's a straight up coordinate basically. But here we're going to use that as an offset. So 0, 0, so the first 0 is the horizontal offset, or the X value, and then the second number is the vertical offset, or the Y value here, and then the very last value is our tile ID. So the tile that's going to represent the actual graphic for the sprite. So here we're going to say that tile 0, or tile ID 0, is what this sprite will be using for itself. And as you remember, a sprite is either 8x8 pixels or 8x16 pixels in tall mode, and here we're using tall mode. So here that's what we're defining, and we're going to have groups like of these put together in a row to make the entire Metasprite. So we're defining sprites to create a bigger, more, or a compound sprite of sorts, and that's what a Metasprite really is just a collection of smaller sprites, or a collection of sprites, I should say, not smaller sprites, but a collection of sprites. So, and as you recall here, we actually only have 2 sprites for this. So here's our first sprite, 0, 0, 0. So we're getting, or the origin point is at 0. So we're starting at 0 here for the X value, and then for the Y value is at 0. And then if we move over to the next one, as you can see, our X value has changed, so it's moved over to the right. As you recall, if you go positive, you're moving to the right. If you go negative, you're moving to the left. So the second sprite, that in a tall mode, remember, is now 8 pixels to the right of the other sprite, but it has the same Y value of 0. So it's not moving down or anything. We're just moving the second sprite to the right. So then that's what these 2 numbers are. So we have 2 sprites that make up the entirety of Miss Pac-Man as a Metasprite. So these little sprites make up the whole thing of Miss Pac-Man. So that's what these numbers are. So as you saw over in SMS Tile Studio, 0000, that's X, Y, and then the tile ID, which will be the first tile in the VRAM. And then here in the second part, that's where we define that X for the second sprite's to the right of the first one, and it's still at the same position vertically. And then as you can see, this 2, that is the tile ID for the next set of graphics for this sprite. And as you can see, it goes from 0 and then to 2. Why does it do that? Normally, if it was in normal mode, it would be 0, and then the next sprite would be 1 in succession. But since we're in tall mode, we skip over the next definition of the tile. We don't need to define the next tile. Since it's on tile mode, 0 is fine, so that would incorporate 0 and 1 in actuality in our VRAM. And then for the next sprite, we would just skip over to 2. So it would be even numbers here that we would be applying for the tile ID when we're in tile mode. And we're defining 2 sprites total in tile mode as we went over in the editor. And then at the end, we're going to use this constant that's given to us from Devkit SMS, saying, okay, this is the end of the definition of this metasprite. So metasprite end basically tells Devkit SMS this is the end of where we're defining our sprites, and that's all that is to it. So this would be the first frame of animation that we did here in SMS Tiles 2. So it would be that one, and then, or this one I should say, and then we go to the next one, and the next one, and the next one. So we have 4 frames total, and that's what these are. And as you can tell, as we get to the next sprite, typically we would have this in VRAM in succession, but since we're going to be streaming it, we in all actuality only need 1 sprite total for the player instead of all these animations, because we're not going to put these other animations into VRAM. We just don't have enough space for it. But in a typical setting, you would define your animations or your frames of animation, and you would define the sprites that would be in each one of those animation frames. And then here there's a collection, there's a pointer array that points to each one of those frames that we have defined previously, and that just makes it convenient for us to pick which frame is going to be showing next after the duration is up and we need to update the frames of animation. So I want to give a background on that, and that's what this is part of that definition of a metasprite, but we're not going to be using this just yet. You'll see that more when we define the ghost source. What we're going to do though is we're going to define player 1 and player 2 sprites. So player 1's sprite only needs the first 4 tiles, so 0, 0, and 0. There's no offset from the origin for the sprite. And then here is the same thing that we just looked at, where the next sprite is to the right 8 pixels, and then it uses 2 as the next sprite and tile ID for its graphics. For player 2, it's going to be right after player 1, so that's why after 2 we define player 2 sprites as the next tile ID as being 4, and then its other tile ID is going to be 6 in this scenario. And to, I guess, better visualize that again is that here we left these 8 tiles free and VRAM, or we will be. And so the first player 1 sprites will be the tiles will be these 4 tiles here. So 0 and 1 and 2 and 3 would be the graphics that would be used for player 1, and then for player 2 it's 4 and 5 and 6 and 7 that would be used for player 2's tiles. So we would update these for player 1 and we would update these for player 2, and that's where those IDs come from, 4 and 6. And this is all we need to define for the sprites for player 1 and player 2. Since we're streaming the data, it's going to be a little different on how we're going to update the animation frames. So the next thing is that we're going to bring in some definitions of where these frames of animation will be in VRAM when we get it. Oh, I shouldn't say in VRAM. This will actually be in our bin, our binary file that we already have created. So when we took this and we exported it as a binary file for the player, all we're going to do is when the frame needs to be updated, we're going to dig into that resource that we created over here under assets. We're going to dig into this resource. We're going to point to where the next frame starts, and then we're going to use that data, which would be, let's see, I think 128 bytes. We'd stream 128 bytes to the VDP to update the animation. So instead of having it in tile IDs, now we're actually using the raw byte amount to update the player. So, and I'll go over that. So for the player one write, which is our first animation based off of what we have here, it's going to start at 0. So the byte data that we have already exported, we're going to point to certain parts in here that will get our next frame. So the first one will be 0, and since each one of these tiles here, so an 8x8 pixel tile in VRAM is 32 bytes total. So what we're going to do is, if we have 4 tiles, well, that's 4 times 32 is 128 bytes total. So our first frame animation starts at 0, but when we get into the next frame of animation, that's 128 bytes away from this first frame of animation. So that's what we're going to define here. So our first one starts at 0, but then our second one starts at 128, and then our third frame of animation, if we go back in here, we'll start at another 128 bytes away. So we'll start here, and that's 256 bytes. So we're going to start at 0. Our second frame will be at 128, and then our third frame will be at 256. And as I showed in the animation that we have here in this sprite, we actually repeat that last graphic. So what we're going to do is we're going to sort of ping pong it in a way. We're going to go the first frame, second frame, third frame, and then back to the second frame. And that's how we're going to define our animation here. So that's where player one write is, and then again we'll go on to the next one. We're going to figure out what that next starting point is for that animation. So here we went from 0, 128 to 256. Now if we see, as we can see here, now we have the graphics that are going down. There's 3 frames for that. So our next, once we add another 128 to it, that gets us to 384 now. So 384 for this frame of animation, then another 128, which makes it 512, and then another 128 makes it at 640. So that's what this one is at, where this graphic starts. And again, we're going to ping pong it, so we're going to go back to the middle one. So 384, 512, 640, and now we're going back to 512 for those 4 frames of animation that make up the player for when they are going the direction, when they're going down in their direction. And then it all just continues from there again. Then we go to the left. As you can see, we start here with these 3 frames of animation for left, and we just continue from where we left off from 640. Now we're adding another 128. That makes it 768, 128, 896, 128, 1024, and then again we're ping-ponging back. So it's the same thing. We're just doing that all for each one of these animations, so we know exactly where it lies within our binary data when we go to bank switch to it. So again, bank switching is very important here. So that's all the frames of animation for player one for each direction. And then there's a point where the player gets chomped by a ghost and it's kind of spinning around. We all have all the graphics for that, so we just need to pick the graphic where Miss Pac-Man's mouth is open, and we're going to start with the animation facing down. So here 512, all the middle ones are the ones where Miss Pac-Man's mouth is in that intermediate animation. So we're going to pick 12, that means it's going to be down, and then 896, as you can see, is left, so it's going to face down, then it's going to go left, and then 128, and now it's going to go up, and then it's going to keep on continuing that animation. So down, left, up, and then right, and then again down, left, up, right, down, left, and then finally it rests where where Miss Pac-Man is facing up. And that's our animation there. We can just use the information we already have here to create that animation. And then we have 2 additional points in memory that we have to point to, which is the marker. So we have the player 1 marker down, which is here, and player 1 marker up, which is here, which we would have to count every single one of these frames to get down here. So how we could do that, or how we could calculate where that would be then, is if we just take each one of these. We know each one of these is 128, so we take 1, 2, 3, 4, 5, 6, 7, 8. We have 8 across, and then we have 8 times 4, which is 32, and then that would be 33, and then most likely that's the number we need, 34, I believe. So we take 34 and we times that by the number of bytes that each one of these things are going to be. Yeah, we'd have to add another one, so it'd be 35, if I'm correct. So 128, is that right? Yeah, so that'd be for 448. I'm sorry. Yeah, it would be 33. So what we called originally. So 33 times 128. It's going to be 4224, because that's where that data is going to start. And then we would have to add. This would be 4224 is where the byte would be, and then we have to add one more to that to get to the next frame. So we would go in here, and then we would add 128, and then 128 again, because it would be 2 frames away. And there you go, 448. It would be the amount of this one and the amount of this one, and these 128 here and a 128, and then that will give you 448, which is where our player 1 marker up is located. Hopefully that makes sense. Basically all I did is count all these frames up to here. 33 times 128 gave us our first one. Then we had add an additional 128 and a 120 here to find the position for this one. So that's what it would be, the actual byte to this data throughout this entire sheet here. So as you remember, we exported this sheet, and that's where those graphics would start, and that's where what we are defining there. Okay, here's now we're defining player 2 frames, and you can see that continue from 148. Remember, up was the last thing for player 1. So this up from here, now we're going to start getting player 2's frames starting here. So we would add 128 to this number, and that would give us 1536, and then again add another 28, 128, another 128, and again we're ping-ponging again with that last frame. Same thing we did up here, but we're doing it for player 2. And then lastly, for those frames, we have cutscenes where Pac-Man's involved, and again we're going to point to the data here where Pac-Man starts. So Pac-Man starts, this is, we have what, 8, 16, and then what, 3, this is 24. So, you know, we take 24 times 128, because each one of those animations is that, and you can see that's where we're going to start Pac-Man at 3072. And again, we're going to add 128 because it's 4 tiles, and each tile is 32 bytes in size. So there's 4 tiles. 4 times 32 is 120 bytes. That's where we're getting that from. So you take that 3072, we add 128, and then we add 128 again, and then we ping pong again. And here Pac-Man doesn't have a down animation because there's nothing in the game where he needs to have the animation where he's facing down. That's to reduce some size there. That's the reason why I did it. That's why there's only 3 facings. Okay, and that's all we need to define for our actual sprites and graphics for the player. And the reason why we have Pac-Man here is because in those cutscenes, player 2 will be sometimes Pac-Man in those scenes. So to go into further detail about that. So our first function for the player is to reset player variables. This will be for player 1 and 2 typically. The current, and then we'll reset the current player. Current player is that global variable is looked at when the game engine is actually running. Typically when the game is in either 1 or 2 player mode. Team mode, it would always be index player 1 for the current player in that scenario. And then we have our default lives as being 3, so we're resetting that global variable as well. Then the player lives and the current stage are on, and their scores will be reset. The stage, the global stage that we're currently on, will be reset. Their pellet count, so the amount of pellets that the players consume, will be reset. And this P1 start is a flag, as I went over with globals, where the first time you play the game after you press start, it will play some fanfare and do something a little differently with the text. That's what this flag is for. So we're going to set that flag. And then the ghost mode, which was the timer that flips from the chase mode to the idle mode. And then also setting that ghost mode as that. So this is a timer for it, and this is the actual mode. So that's all that's doing there. It's doing some resetting. And then the next thing, there's typically 2 things that I have with each one of these entities or source code, is that I have a loading function and then I have a updating function. And when I say set player, it is essentially saying we're loading the player. And that only happens usually during the start of a game state before it runs anything. So as you can see, I have like, I don't know how many parameters. It's 1, 2, 3, 4, 5, 6. Like I said in my previous video, usually you want to keep it at a maximum of 2 parameters, but here you have more than that because this is done during the loading phase of a game state. It's not being continuously ran, so I believe you can get away with having more parameters in those scenarios. I haven't really seen any adverse effects in doing so. So here I have about 6 parameters, and here I'm defining the index that's being used here. So this could be player 1 or player 2, or it can be, Pac-Man or something. So we would define the index, and then here we would find that the types, and again that's all going back to the define. So here you would put whatever these indexes would be here, and then you would also put in whatever the entity type. So here we would put in either player 1 or player 2, or it would be Pac-Man in certain scenarios. So that's what that type would be. We already have those defined, and that's what we would enter there. So we would enter those 2 constants here, and then another constant, which would be our direction. So we would enter whatever the default direction is when the player starts, which typically is left, and going on again. So state, another define a constant that we would feed it. Our state would be the ones that we have defined here in the beginning. Any state, whatever it may be. It may be idle, it may be none when it starts up, but then it would be one of these constants for the state. And then the X and Y position just means where we're going to put the player on the board when we start up. So whatever that X and Y may be. So we're going to set those all up. Remember, we have those entity properties. We're going to use that index for the one that we want to change. Again, going back once again, showing what those indexes are. They're hard-coded here, or they're defined through constants. So that's what we're going to hand it. And we're going to set up all our things. Our substate will be wiped out here, or reset. And our any frames will be reset. So the current frame that we're on, which honestly, here we set it to 1 because we don't want it to be 0. If you have it to 0, that means we're going to have it where Miss Pac-Man starts with this frame and animation. And what we want to start with is this one. So we set it to 1 here because, as you remember, everything starts from 0. First frame 0, the second frame is 1, and that's what we're doing here. And here, this entity frame duration, as we went over before, is a signed car, so it can be a negative. And here we're going to set the negative because on the next iteration when the game actually starts up, it'll increase that by 1, or it'll look at this and it'll automatically change the frame based off of what we have here. So it's reset to -1 at this point. This is a big one. This is the update player tiles. So this is the function that actually streams the data into VRAM when we're creating the graphics for the player. So right off the bat, as you can see, I call the ROM bank switching method that Devkit SMS provides. If you're going to go to your binary data, your asset data, whatever it is, compressed data, whatever it might be, you first have to bank to it. You have to switch to where that data is. And again, Devkit SMS provides this, all the constants, everything you need when you use assets to banks. It provides all that information for you. So we're using assets to banks, variables and constants that it created for us when we created the assets through through our batch file, which was the assets builds file, or when we just compile, it's creating those things for us. But so here we're going to switch to that bank, and the bank that we're looking for is those player tiles that we created, which was exported here. So our player tiles, the actual data, the image data, we're going to go and grab that, and we're going to put it as our current bank of data. So we're going to switch over to that. Since to save on processing power, since streaming is a little intensive depending on how many tiles you stream in, we're going to actually flip-flop the animation between player 1 and player 2 to save some processing power, because when you're in team mode, you want to try and use as little of processing power as possible to have enough screen time to process everything else. So what we're going to do is on even frames, we're going to update the graphics for one player, and then on odd frames, we're going to update the graphics for player 2. So that's all we're doing here. So we're looking at this frame counter, and then what this &1 is that we're going to look at a certain bit in the frame counter to see if it's odd or even. And then based off of that, we're going to update the player tiles for player 1. So here at 0, that's where we're going to start updating. As you remember, the player 1 tiles are the first tiles in VRAM. So it will start at 0. And then what we're going to do is, again, we're going to use this pointer into the player tiles data, and we're going to get the player frame that was set up before this gets called. So player frame, again, is this a short? All that is the current number that we grabbed from here. So whatever number that we grab through one of these, that's the number that's going to end up here. So for our current frame, and in the beginning, it's going to be 0 for the player 1, but as the duration reaches its threshold, it's going to update this number. So here we're saying, okay, we're going to go into our player tiles data, which again is this big old sheet here that we have, which is 4,736 bytes total. And we're going to get whatever the current player frame is at that point for player 1, because player 1 is 0 in this index, player 2 is 1 in this index. So remember, this is if we go back to the definition, remember it's an array, so there's actually 2 values in there, and there's one unsigned short for the player 1 and one unsigned short for player 2. So for player 1, we're going to get whatever that current player frame is, and that frame number will be something along the lines of in here, whatever number it is currently at that point. So that's all it's doing here. It's going to call unsafe, so I'm going to call this method immediately after VRAM And as you can see, the VRAM mem copy 128 takes a destination address, which would be a byte, whatever the byte address would be there, and then the actual source or the pointer to the source, as you can see, has a star in front of it for the source. So that's where we're going to point into our data where the frame actually starts. So and that's what we're doing here. So it's always going to be at 0, so we're never going to have to change that. And this is just, again, going to our player tiles byte data, and we're going to point to where the first, or where the frame should be at that point. And then this is all this is going to do is going to copy 128 bytes and then send it over through the port to the VDP, and then in VRAM this will be updated. So that's all this is doing. And we were copying 128 bytes from our player tiles data for the current frame in VRAM at 0. And then here, this is for player 2. And there's some other conditionals here. We want to have some conditionals because we might not have to ever update the player 2 while we're in the game engine mode. So we can, there's cases where we can ignore it, like, you know, here we're just checking if it's in team player mode, or if it's player 2 that's playing, that we're going to actually use these graphics, or if it's something that's outside of the game state of running the game engine, like we may need it for a cutscene, or we may need it for like a demo or a title screen or whatever the deal is. So here we're doing some additional condition checking before we actually commit to taking the graphics for player 2 and then putting them at 128. So as you remember, here we did for player 128 bytes that are going to go into VRAM. And then here we're going to do the same thing, but we're going to set it after the player 1 data. So we're going to copy 120 bytes at 128, the byte 128 in VRAM. So, and again, that would look like you would have, so here's your 4 tiles, and here's your 128 bytes, as you recall, 32 bytes, 32 bytes, 32 bytes, 32 bytes. That's 128. So after this 128, and then we put in player 2's 128 bytes here. That starts at 128. So that's what we're doing here. So the same thing here. We're going back into the player tiles data, and then instead of using player 1's frame, and now we're going to use player 2's because we're using 1 here. So that would be player 2's current frame of animation. And that's all this does, but that's where all the streaming happens. Update player sprites. This is just basically drawing our meta sprite that we already have defined. So here we're going to check, all right, if it's got an any state where it equals none, we're not going to bother drawing the sprite at all. We're just going to bounce out of this. So essentially this makes it that the player won't be drawn to the screen at all. We're going to set a visibility, which again, we got that from our entity source code over here, where we're going to check the state of the entity when it comes to if they're on screen or above the screen or below the screen or anything. We're going to set that visibility every frame here. So, and then here I use 2 local variables. And before in our previous video, I was talking about being careful about how many of these local variables that you should define. And typically the suggestion is only have a maximum of 1, and typically you would use that as an indexer. And with this certain function here, I did a lot of testing on this because, again, with every new function I make, I isolate it and I test to see, you know, how many cycles is it using, how many scan lines of does it take to process this, you know, this certain function. And I found that if I define these 2 here, which I use quite frequently down the road. Here you can see I change Y, and then I have X here as a definition instead of using the entity X and then just doing it that way with the offsets. Here I'm offsetting some stuff. I find that this actually got me a little bit more performance. I think it might have bought me another, I think instead of like 12 lines of, or scan lines of processing, it was actually 10 when I did this, and I defined more than one local variable. And here I did get a little bit of savings. And each line that you can save is actually a big deal. I know it doesn't sound like it's a big deal, but when you go to see how performant your code is, you'll realize how important saving every little bit of processing or making it as optimized as possible really is going to help you down the line when you start putting everything together. So here all I'm doing is I'm getting the NEX, so that pixel value of where the player is currently. And the reason why I take -8, and here actually I could define this -8 if I wanted to. All the way back here I could put it in as a negative value for the origin, but here I just do the math. So what I do -8 is the origin is for the X and Y is at the top left, but I want the graphic to actually be popped up about 8 pixels and then popped to the left 8 pixels so that the origin point is in the center of the graphic. And to better explain it, so as we see, the origin would be here typically, but if we move to the left 8, that puts it in the center horizontally, and then if we move up 8, I'll put it in the center horizontally within the game maze, because there's going to be some other offsets that's going to be applied here. So that's why this is done. We have -8 to the where the origin would be for the X value, and then -8 for the origin for the Y value. And again, you'll see that more in the play because of the way that things are offset as the origin point going through the maze. So, and the scroll Y here is that offset that the scroll has on the stage that we talked about before. It can be anywhere from 0 to 96, so we're going to apply that offset here based off of whatever the current vertical scrolling is at a point. So that's what all this does at this point. Sometimes you want to put on the global vertical amount offset based off of where the scrolling is happening and everything else that's happening to the other entity. So as we scroll down, all the other entities that are affected by that scroll actually have a value where they're going up, and then vice versa. As the scrolling is happening going up, then there's a scroll amount that's applied to the entities that makes them go down. So it looks like they're in sync with the scrolling. So that's what this is, and this only is applied if the scroller is not the current player that's being processed. So here we're saying is the scroller, if it's not this player, then we're going to apply that scroll amount. So it could be a negative value here, or it can be a positive, but we're just going to add it. Or if it's that it's none, then that's going to be applied as well. In those scenarios where it's none, or where it's, not none, I'm sorry. If it's not none, we're going to be looking for like an auto scroll or something of that nature. So that's where this would be applied. And again, here we're going to check if what the visibility is. If it's out of view on top, we're going to offset the Y, so the vertical position, we're going to hard code it at 0, because it will become a marker at that point, and the marker vertical value is hard coded to the top of the screen regardless. So that's what we do here. And if it's out of view at the bottom, we're going to set the vertical position of the marker hard coded at the bottom of the screen. So, and that's where 176 comes into play. And then at the very end, we're going to actually add our meta spray, and this is where Devkit SMS provides us the function to place the metasprite on the screen. So here we're going to hand it our X value and our Y value that we pre-calculated. And then we have to hand over the collection of sprite definitions, and that's where our player 1 sprite definition at the very top comes into play. So we're going to hand it this for player 1. So if the index is player 1, or if it's player 2, or Mr. Pac-Man himself, we give it the player 2 sprite. And that's all that is to that. Next one is update player frame. When it comes to streaming, the adding the sprite is usually less intensive, and updating the frame becomes more complicated when you're streaming. If you're doing it the other way around, it typically is that the sprite logic is more complicated and the frame logic is much shorter. So, and we'll see that because again, the player, it's using the sprite methodology, and the ghosts are using more of an in-memory methodology. And typically when you have a stream sprite, all your details within the actual update of a frame is a bit more complex. So here we're going to check if we're in team play mode, and this is a special pause. So you don't want to update the animation if the other player, so if there's 2 player and you have team mode, if a player gets chomped or there's a pause for the game, this is a special pause here, that number 2 that I was talking about way back when. We still want to interrupt the action of the other player. So the other player should not be able to animate during that pause, and typically it would if we didn't have this check in here. So we're going to check if anything other than the dying state, and we're in team mode, and this has a special pause. So if we don't want to update the animation, so we're going to return. So that's what this logic does here. Here we're going to, as you can see now, we have these 2 minuses in front of a variable, and what this does is it pre-calculates the subtraction here, or pre-applies a subtraction to here, and then we're going to check if it's greater than -1. So we're going to reduce the entity frame duration, so that means the timer it takes for us to move to the next frame. And if it's greater than -1, then that means like we're not ready to update to the next frame, so we're just going to bounce out. But once it becomes less than or equal to -1, then we're going to update the frame. So here we're just checking, all right, are we ready? If we're not, then let's bounce out of this. We want to try and bounce out of all of our functions as soon as possible when it becomes something that is a performant code. So we want to do our checks, or checks that would normally bounce us out of a function early ahead of time, and so that we don't have to do some needless checking, because that costs cycles, especially when it comes to something like the Z80 and 8-bit processing, or 16-bit processing, whatever way you want to look at it. We want to make it that is as optimized as possible. We're not doing needless checks. We want to check certain things and then be able to get out of the code immediately if those conditionals are true. So here, the rest of the code is basically saying this is what we're going to do now that we have to actually change in the next frame of animation. So here we're going to get our entity frame, so whatever our next frame will be. And all this is doing is checking. It's like, okay, if we add 1 to our entity frame, that the value that is currently, is it greater than our maximum frames that we have? And we can use modulo typically for this sort of thing. So a modulo, you would check whatever your max frames are, and then you modulo against it, and then see if it's equal to 0 and that sort of thing. And you could do it that way, but we're not going to use modulo here. We're just going to use just a shorthand or a ternary conditional here. So first we're going to see if, all right, if we add the next frame, is it going to be greater than or equal to our maximum frame that we have? And here we're checking the maximum frame amount. So typically all our animations are only going to be 4 frames, as you saw previously. The only thing that's going to have more than 4 frames is if the character is currently dying. So circling around is going to be 11 frames based off of what we defined earlier. So here we're saying, okay, is the player dying? If they are, then the maximum frame is 11. If they're not, then the maximum frame is 4. But at any rate, if we are greater than or equal to that maximum frame, then we're going to reset it back to 0, so the start of the animation. If not, we're going to add 1 to our next frame, so we would get our next one, whatever it is. So if we're at 0, then the next frame would be 1, and then after that duration is up again, it'll be 2, and then when the duration's up again, it's 3, and then when the duration's up again, it'll check if it can go to 4. Here in this case, it can't, because 0 to 3 equals 4 different frames. So here we're checking, all right, it was greater than or equal to 4. Then we're at the end of our animation. We're going to reset it back to 0. Otherwise, we're going to increment or advance to the next frame. So that's all this does. Increment frame based on state. Resets if it's over the max frame count. And then we're going to have a switch case statement. Now that we have the frame that we're going to process next, we're going to check the entity state. So any state is some of the stuff that we defined in the global, or the defines when we went over the defines source. The player can be dead, the player can be dying, the player chomped, is it idle, are they moving, whatever the deal is. So that's where we have all these conditionals. So if the entity state is that the player is dead, we don't want to animate into anything else frame-wise. We want to keep it at frame 2. So every time it comes in here, frame 2 will be the frame that the dead state will be. And why did we pick 2? Because we're going to use that 11 frames of animation. So it starts in that frame for the dying state. It starts at facing down at 0, then facing left at 1, and then facing up at 2. So we're just gonna, since dying happens before dead, we just keep the dying animation. So we're just gonna keep it at 2. So when it's dead, and as you can see, I have no return or break here. Normally you have case state and then you have a break, and then you break out of this. This is a fall through. So when this happens, it falls through to the dying state. And again, that's the reason why we use frame index 2. So it's going to fall through into dying, and then here at dying, it's going to break out of this because we haven't seen anything like that yet. Usually either we're returning back from a case or we're breaking from a case. Here we're actually falling through. So when the entity state is dead, we're going to fall through into the dying portion of it, and that's what this means. So we're going to keep it at the facing up animation, or frame of animation. Here we're actually setting the duration for the next frame. So again, when the player is dying, and we go back to this, I'll start here at 0 again, which is facing down based off of this. So it's going to face down for X amount of frames, and that duration is where we set there. So it will face down for 6 frames, and remember, use defines here because we also want to be able to support PAL later. So here we're saying times 6, so that'll be 6 frames that it has, and then with each loop on the V blank, I'll de-increment this. This is where it gets de-incremented. So de-increment it from 6, then I'll go to 5, then 4, then 3, 1, 2, 1, 0, and then when it de-increments again and it's less than 0, instead of kicking out of this, then I'll do this processing for the next frame. So here we're actually setting that duration here. So for the dying state, each frame takes 6, or frame of animation takes 6 frames of processing before it changes. And then here we're just setting the player frame that for the streaming portion, and we're going to go into those arrays on the frame that we're currently on for the actual player that we're trying to set up. So it could be player 1 or player 2 on this index, but here we're checking it, and we're going to get that it's any player 1 here, or it could be any player 2. Again, we're just going to go into these frames that we already defined, and we're going to pick the next frame based on the current frame here. That's all we're feeding it. And again, we look up here, player dying, this is what we're going to look into, and then this is the one that we're going to increment. And then if it's at 11, we're going to go back. Or in this scenario, we're actually only going to play it once, and then that'll be that. So, and that's what that does. And then it breaks out. So this is all one chunk of code in reality. And then we have some more fall through. Here's another one where we have one chunk of information because we have some fall through. So if the end state is that the player got chomped, or if the end state that the player's idle, we're going to use the first frame. We're always going to hard code that first frame if these two states are the case, because in either one of these cases, if you want the frame where they have their mouth open in that one, we want this one here. So 0, 1. So 1 is the frame in this case that we want to use based off of the graphics that we have set up. So that's what we have. It's going to fall through into default. Default means this is what happens if none of the other cases are true, and we can still fall through it if we don't define a break or we don't define a return. So here we're falling through, and then we're just going to let default handle it, which really the only two types of animations that Miss Pac-Man has is either dying or the moving sprite, where it's constantly moving and chomping. Again, the only times we don't want to do that is when it's idle and when the player got chomped, and then we want to hard code it that it's only going to have that graphic where Miss Pac-Man's mouth is open in that one frame. So again, we would set up the entity frame duration. If it's if we're going through a scene, I want to make the animation slower. Typically, when Miss Pac-Man goes through the game stage and it's in the actual game engine, its mouth, or her mouth, opens and closes very, very rapidly. But in the title screen, when she comes across into the center as she's being presented, the chomping animation is much, much slower. So here we're going to check if we're in a scene, which would be a cutscene or a title or whatever. If it is, we're going to give it a little more time before we move on to the next frame of duration. So we would wait 2 frames before going to the next animation frame. But typically, while we're in the game engine, we want it as rapid as possible. We're only going to wait 1 frame. Actually, we can wait no frames if we wanted to. That would be too fast, though. So 1 is just the sweet spot. So we're going to give it 1 frame of duration before it updates the frame. So that's what we're doing here. And then based on the actual entity type, so if it's player 1, player 2, or our default, which would be Pac-Man in this case, we're going to do some additional logic. So if it's player 1, and based on the visibility, here's where we're going to actually use the marker. So here we're saying, okay, if it's out of view at the top, the marker that we're going to use for our next frame of animation is the player 1 up marker. And this won't happen at this time, but it is set up in logic that if in the future player 2 can also scroll the screen to the point where player 1's off screen, this will handle that. So if player 1's off screen, we can set that marker. And again, if it's out of view at the top, we'll use the upper marker. If it's out of view at the bottom, we'll use the down marker. And then it will pop out, because then there's no reason to do any more of this logic. Again, here we already set what we needed, so let's get out of here. We want to get in this idea that like the house is on fire and we were trying to find the shortest exit to get out of the house. And that's basically what we want to do here. So you want to do the least amount of conditioning, least amount of processing. Once we know that this is what our frame is, there's no reason to look at anything else below it. So we're just going to return after we set that player frame. And then if those aren't true, as in if there's no marker being used, then we're just going to do in our normal frame of animation. So whatever direction we are currently facing, or the entity that, the player 1 or player 2, whatever direction they're facing. Here's player 1, and we're going to set that frame again for those ones that we define: the player 1 right, player 1 down, player 1 left and up, and then whatever the current frame index is. So that's what we're going to do there. And again, those were defined here. So those will be our normal animation. This is for our dying animation. And then these are our markers, which, as you can see, have no animation. They're just one frame, and they're always the same frame. So, and that's what we do. And then that's for player 1. Player 2 does the exact same thing, just for player 2, where we're checking and setting up our frame. And then for our default, this would be Pac-Man himself. There's no point in checking the marker up or down logic, because he's never actually in the game engine. And the only thing that he's in is one cutscene where Miss Pac-Man and Pac-Man are being chased by ghosts. So, and again, we didn't have to use the down animation because that doesn't happen anywhere in the game. We just have 3 of them, so depending on whatever that entity direction is for Pac-Man, we set that frame here. And again, you can see it's on player 2's tiles. And that's it. That's all it is for update player frame. Set player next stage. This is called from the game engine. This is when the player, whether player 1 or player 2, goes into the next stage. There's some things that are reset there, some things that are incremented. As you can see, going to the next stage, we're going to take the player 1 stage and we're going to increment it, because in 2-player, it'll be alternating between player 1 and player 2. So we have to keep track of where each player is, because they could obviously be on different stages from one another. And resetting their ghost entity mode in the timer and their pellet counts and all that stuff, that gets reset here, and that's used from the game engine. Player eat pellet. So this is when, I don't know why that's there now. Anyway, this is when the player rolls over a pellet, and we now have to do some things based on that. So they roll over a pellet. What we're gonna do is we're gonna check if the pellet count at that point, is it at 70? Is that at 170? The reason why we do that is at 70, we're going to roll out the bonus. So the bonus is going to show up in one of the 4 predetermined places for it to appear. I know I said that there are stages when there's only 2, but there's still 4 options. So even if there are only 2 places for the bonus to enter or exit, there's still 4 options to choose from. So even though they duplicate each other. But besides that, so it's gonna, at 70, we're gonna roll out the bonus, and here we're gonna check, okay, is this the first time it's coming out, or is this the second time? Because the bonus comes out twice. It comes out at 70 pellets, and then it also comes out at 170 pellets into the board. So here's this checking, okay, which one do we have to roll out in memory, because when you get later into the game, the bonuses become randomized from the first time it shows and the second time it shows. So here we're going to denote which one is being pushed out. And then we're going to set our bonus, so that means this is our load for the bonus, and that the state of it is the only thing that we need to hand in. The state saying it's entering the board for the first time. And then the other states would it being, that it's rounding around the ghost house, and then when it's leaving. I'll have to see why that's. Huh. Don't matter. We'll get to that then. So now that we've seen if we have to set the bonus, and we'll do that there. And then here we're going to set that map tile based off of the common source. Here we're going to hand it the index of the player, so player 1 or player 2, so we know which map to update. And then we're going to set the tile to empty, which here is 256. So that's all this does, and we went over that previously. This is where we're actually going to increase the pellet count depending on the mode that we're playing. So if it's in 2-player mode and the index is player 2, we're going to update player 2. In all other modes, team mode or player 1 mode, we're updating player 1 pellet count, and we're setting the current player count. That's what this is. This is a global. It's going to set the current player count to what we've updated for player 1 or player 2, and that's all it's doing there. Here we're going to actually make the sound of the pellet being consumed, and then setting it that it plays on channel 2. And then here we're going to check, okay, is our pellet count that we have for our current pellet count, is it greater than or equal to the maximum pellet count that needs to be consumed for the current stage that's being played, whether that be player 1 or player 2. So we're going to check if it's greater than or equal to that pellet count. And we're going to run this routine where we stop the music altogether and the sound effects. We're going to put it in pause 1. That means everything on the screen is going to pause. And then we're going to set our current player to idle. And we're going to reset the accumulator, which was going to be used in the engine to flash the screen. So here we're just making sure that it's reset before we go and use it. And then we're going to set our substate to 6, which is the substate again on the game engine. And then this substate 6 means that the stage has been cleared. So it'll run the stage clear functionality when it sees that it's substated at 6. So, and that's all we do here for the ePellet portion. Okay. Moving on. Here's where we're actually checking if the player rolls over a pellet. So here again, we're giving it the current player index. And then here we're also giving it the tile ID. So we're going to check, is the tile ID the tile pellet? So as we define here is 258 when we look back at the map. We can go to the map and we can see that 258 is the pellet. If we can see here, hold on. This is 256, 257, 258. That's the pellet. Is it a pellet? So a normal pellet. If it is, we're going to add that score to the in-memory score array and update the screen if necessary, as in if the score is visible. We're going to update it. And then we're going to call that player ePellet, which we already defined up here. And then we're going to return 1, saying that yes, the tile that we were given is a pellet tile, and this will mean something special. When we return 1, that's just saying true. So that's for a regular pellet, and then for an energizer pellet, which again is 257, we're going to check if that's the case. So now we're going to set up our global energizer timer for all the ghosts, and then we're also going to get whatever that half amount is for that timer, because that's when we'll start blinking the ghosts, saying that they're almost coming out of their frightened state. So that's what we're doing here. And then the ghost point accumulator gets reset. So those are the global variable that's keeping track of how many ghosts you chomp after you've eaten an energizer. So it will start at 0, and then as the ghosts get chomped, it will double up the score every time. So here we're just resetting it because we just ate a fresh energizer. And then here we're going to add the score. Eating an energizer is 50 points, so as versus 10, again for the current player that's being processed at this point. And then here we're going to play the energizer sound as long as there's some duration for it. So the ghost frightened durations, not all of them. As you can see in that array, we have 6, 5, 4, 3, 2. Those numbers are supposed to be seconds, and you see somewhere 0. If there's 0, then we're not going to bother even playing this track. Player ePellet, again, same thing that we did before. So we're going to do all that business. And then set all ghost states. So what this will do is it'll make all the ghosts in the frightened state once we eat this energizer. It'll also set up some other additional data based off of this. And then we're going to return 1 again because we ate a pellet. If we didn't eat a pellet, then all this stuff gets ignored and return false. We didn't eat a pellet because that's what we're checking for. Did the player eat a pellet? Here is a function that we'll use later. Get sign. We can actually create a C macro for this if we wanted to, but I decided to make it a function here just to go over it a little bit. So here we're just going to hand it a signed number of some sort, and we're going to check if that number is, if it's greater than 0, then we're going to return 1, a positive 1, and if it's less than 0, then we're going to return a negative 1, and if it's equal to 0, then we're just going to return 0, and we'll use that later. Set tile pixels. So we're going to hand an index of the player that we're currently looking to change some information for. So here, any pixel X, we're essentially modulo the amount here. So for every tile that we go into, we start counting the pixels that are in that tile, so the subpixels within that tile. So there would be a grand total of 8. So here we're doing some creative masking. So we're going to set that any pixel X here and that any pixel Y value there, and then here if it's less than 0, we're going to reset that value to 8. And same thing here. If that countdown's less than 0 for the vertical position, we're going to reset to 8. And then here we're going to see how much destination or distance we have from our any pixel X to the center of a tile. So that center point, or 4 pixels in, we're going to set that distance here, and that for both the vertical and the horizontal coordinates, and you'll see that being played into later. This is part of the corner cutting feature that we have for the player, and that's what both of these really primarily play a role in. here is move entity player. As you remember in our I think it was a previous tutorial where we defined the entity functionality. We're going to apply a different logic for moving the players around. So here we're going to set tile pixel. So we're going to get that information here that we were talking about. Okay, we're trying to find out positionally where the player is within a tile. Then we're going to check if the player that's given here, if they can move in the direction, the desired direction that they want to go into. So, or the direction that's set up for it, sorry. So the current entity direction. So we're going to check if we can move. So that's what this will be. It'll be a 0 or 1. Remember, we defined that function back in the entity source. And then we're going to get the speed for the current player. So we know what to apply. And we're going to return that value later. So, and then we're going to check each direction. Before I had this in the switch case, but I found actually doing an if else if was actually a little quicker. So that's why I did it in this manner than I did it with the switch case statement. Plus it's a little cleaner, I think. So we're going to check if the player's moving right. Then we're going to see if they can move based off of this. So if they can move, or if they haven't quite reached the center horizontally in the tile, they can still move. So if we can move, or we still have more distance that we can get before we get to the center of the tile, we're going to increment the X position. And then for the vertical position, we're going to apply that center point logic on get sign. So it'll either be a -1 or a 1 based off of the current distance that we have, if we got to the center of it or not. So it could be a negative number here. So we could be before the center, or we could be over the center just a smidge. But we want to figure out what that distance will be to the increment for the vertical position. And we do the same thing for all the other directions, except if we're checking down, then we're going to apply that speed to the vertical direction. If we're going left, then we're going to apply it to horizontal here. If we're going left, we're de-incrementing like we did with the entities. So that logic really hasn't changed any from the entity or move entity stuff. The only thing that's changed a bit is trying to see where we are in the center of the tile, and then that will be the basis of if we can move into or corner cut into another tile. So we'll check all those directions, and if none of that is true, we're just going to return that the speed is 0, so we essentially didn't move anywhere. So that's what we're going to tell the calling code. And then at the end, if there was some sort of movement, this will carry the actual speed that we used when we actually moved here. And again, if nothing was moved, then we're going to return 0. This is the move entity player actually moves the player here. This is just a state that we're processing. So if the player is moving, that's what this means, move player. So we're going to get whatever player we are, the current or the desired direction. So this direction is the direction that the player's trying to press into before we check if they can actually do it. So if the player is going through a tunnel, let's say, and they're pressing down, we're going to check if they're able to go down. If not, then certain things happen in these conditionals. So here we unlock the vertical scroll lock. So this is used when the player eats a pellet and they don't move that frame, but everything else in the engine is expecting the player to be moving. And we'll see that in the play later. I think I explained it a little bit, but we'll see how it plays when we get into the engine part. So we're gonna reset the vertical scroll lock here, and then if it's pause, so any sort of pause, so greater than 0, or the when we check that pellet, if it equals that we did eat a pellet with all this information, we're gonna do this code. So when you eat a pellet, you don't move for that frame. That gives it the kind of the feel that when Miss Pac-Man eats a pellet, she slows down just a fraction of a moment. And if the player's eating a bunch of pellets in a row and a ghost is trying to follow behind the player, it actually gives the ghost time to catch up to the player when they're eating a lot of pellets in a row, and to the point where the ghost can actually catch the player and chomp the player. So that's what this mimics. So whenever a pellet is eaten, the player does not move for that fraction of a moment, that frame. So that's what we're looking for. Is typically when the player's moving around the screen, that if they're not eating any pellets, then they'll move like normal. But once they eat or consume a pellet, they will actually lose 1 frame of movement. So, and that's what we're going to do here. So if it's paused, or if we're losing that 1 frame of movement, we're not going to process moving anything because we're paused. We're not supposed to be moving. And then again, if we ate that pellet, we're not supposed to be moving. So we're going to put the scroll lock as 1 if we're actually scrolling. If we're not scrolling, then, or if there's no scroll amount being applied to any of the entities, then we're going to set the scroll lock at that point and return. So basically, it's saying if this is pause, or if there's a something when we eat a pellet, we should be paused. Then we're going to kick out right away. Okay, so then here now we're going to check if we can move in the desired direction the player wants to move in, and we're going to check the direction that they gave us, and that's based off of the input of the gamepad. So if they're trying to move in a certain direction, that's what's given here. We're going to see if we can actually move in that direction here. So here we're going to say, oh, can we move in that direction? If so, then we can set the entity state direction to that desired direction because we know we can move there. And then here we actually move the player as defined up here. Now that we know what our direction is, we just hand it the entity direction that we had it. So it was either the new updated direction, or it will be the direction that was currently in place before we checked if the player could actually move in that direction. So here we're going to actually move them in that direction. So again, this moves the player regardless of what this conditional. So even if it hands back that the speed was 0, it will still perform any movement that needs to be done here based, on this whole thing. But if it comes back as 0, then we don't need to do any more checking. We can set the player to the idle state, so that means the player's not moving, and then we're going to return. However, if the speed is more than 0, we are going to set the state that the player is actually moving, and then we will also check for that warp wrap. So if they, as we discussed in the entity source, so we'll actually perform a wrap through if the player's through a tunnel, and that's where that happens. Obviously, there's no need to check it if we didn't move. So that's the reason why we have it. So it's essentially saying that based off all the things that we did here, we actually moved some sort of amount. Okay, this is going to seem a little big, but it's really not. This is set player speed, and as you can see, I have the preprocessor directive of if defined. So if we defined those NTS that time to NTSC constant. If we defined it, then we'll use NTSC timings here. If we have not defined it, we're going to use PAL timings here, and that's all this means here. So, but it's using the same logic. We just have to change the times for it. So that's the only difference here. So if we are not in the game engine, then we don't really care about this. This gets set every frame. Does it need to be set every frame? Probably not. But the amount of processing it uses is very negligible. I think it might use maybe 1 scan line's worth of processing to do it. So, or maybe even a little less. It's so small that I just let it run every frame. It's more convenient. That way I don't have to condition on when certain events in the game happen. Like one of the events is when a player chomps an energizer, that will change the speed at that point, and then when it's over, then you have to change back. I don't have to worry about any of that. Here I run the function every frame, and it does its thing, kind of like a set and forget thing. So I run it every frame. Does it need to be run every frame? No. You could be more optimized with it. But this is one of those things that is more of a benefit quality of life for me than it is me trying to save the cycles on this one. So here we're going to check again if we're in the engine or not. If we're not in the engine, then none of this applies. If the pack boost is enabled, so that speed boost that you can choose in the beginning of the game, if it's on, then we have a hard-coded value for it. We're going to move double the speed on the base speed, and then our subspeed is going to be 0. And there's no reason for me to do anything else underneath here. So we're going to return, because you don't have to worry about what stage we're on for this to get those speed values or any of that, any of the other stuff that happens with the speed. We don't have to worry about it. So you pop right out. Else, we're going to set our base speed to 1. That's always the minimum for players, I should say. And then here we're going to check if the energizer timer is greater than 0. So while we're energized, we're going to get a little bit of a boost here on the sub speed. And here I got this officially from, I forget what document, someone actually went through, and there's actually values. There's a table, an array for each stage, and for every, I think it's, I want to say 16. I think there's 16 values in each one of these arrays, and it's just a 0 or a 1. So that means in that certain frame in the index, either you move no frame or no pixels, or you move 1 pixel, and we're mimicking that here. So the reason why how I got these numbers, what I did is I looked at each one of those arrays for each one of those stage conditionals. Like on stage 1, it has its own set amount outside of anything else. So when you're in stage 1, that's what it is. And then for levels 2 to 4, it's this, and levels 5 to 20, you get even faster, because these increments mean that we're getting faster. And then they nerf you from 21 on up, and actually bring your speed down to 32. So we start at 32, go to 48, go to 64, and then they nerf you back to this value here. So, or at least I believe that's the case. And how I got these numbers is, since our value is from 0 to 255, I took their array of 16 zeros and ones, and then I figured out what their percentages was, and then I based that percentage off of what that would look like in a value that was from 0 to 255. Because they're doing from 16 values, I'm using 255. So here I'm setting it what it would be as on a fractional portion. So here I'm setting the fractional portion 32 for stage 1, which is, our index starts at 0, so that's how that works. And then, if it's this or this or this, and then this is the else. So we're just going to be checking which stage that we're on, and we're going to apply that subspeed accordingly. So that would be for the Energizer. When you get an Energizer, you're just a little faster. And then the normal state, that means you don't have an Energizer. Your speeds are still affected, so depending on your stage. Same thing as this, and it uses the same range. So here I set this the same way. Now you can see here it's supposed to be 0 for level 1, but I kind of cheated in a way. I put 32 in there, don't tell anybody. It's supposed to be 0, but it feels so god-awful slow. It almost feels like that's not the value. It probably is, but to me it seems so slow setting that to 0, so I actually have that as 32. In reality, if the data is all true from the tables I saw from the dossier and this and that and the other thing, it should technically be 0. But I have it 32. And that's all this does. It sets the speed every frame that is called, and it will be called every frame. And we have 2 more left, and they're not too crazy, so hopefully you didn't fall asleep. And this is the update player state. So this gets called every frame, and this checks the player state, and there's different conditionals on when the player state may change, but it also does some other things outside of that. So since it gets called every frame, I set the previous tile index to the current one. So whatever the current one is, that's what I'll set it to. And then the actual current entity index, I call this every frame that position the tile like we went over in the entity source file. Here we're going to update that index per frame. So, and then here we're going to call that set player speed per frame. So again, this logic. And then here we're going to do a switch case based on the current state that the entity is in, or player, in this case, or players. So we're going to check, here's that fall through. If it's none, or if we're in a scene, then we don't really care. We're going to return. And I did put a break here, which I didn't really have to, I don't think. But if it's any of these, we're not going to do any other processing. We're just going to kick out. If the player was chomped, we're going to set the substate. This is the game engine substate to 5, which means that the player got chomped. So we're going to start running that routine for that substate. Here, if auto scroll the player, so if we're playing team mode, player 2 may have been chomped off screen, and it may be jarring the why everything stopped, because there's nothing visually to indicate any reason why it would be. So here, if player 2 got chomped off screen, we're going to actually scroll to wherever the player 2 is, and then we're going to update the rows. Here's we're calling that safe here because I can't call it during or right after vblank, so we're going to do a safe call here. And here I don't care about the performance here because, again, everything stopped on the game. The ghosts stopped, the players stopped, bonuses, any other logic, all that stuff is stopped. So none of that logic's being even used here, and instead we can make this slow update on when we're going to scroll up or down to get the player 2 into view. So this is where I use that. So there's one, either they're off the screen at the bottom or they're off the screen at the top. So that's what we check here. Else the player is in view, and we're going to use our entity increment timer. So we're going to wait 60 frames or whatever that would be in PAL. And once we reach that threshold, so once we reach those 60 frames here in NTSC, that's what we're going to keep checking. Once we reach that threshold, we're going to set all the ghost states to none. So we're just going to basically not render them anymore. And then we're going to set this state of the bonus to none as well, because you don't need it. Again, let's essentially say don't draw it anymore. And if the index is player 1, we're going to do the opposite. So if the index is player 1, we're not going to draw player 2 anymore. Else, if it's player 2, then we're not going to draw player 1 anymore. So that's basically what we're saying here. And then we're setting our entity state to dying. So here, chomp this means the initial, when the ghost actually chomps the player for the first time, everything disappears, and the player pauses just for those 60 frames, and then and that's what we're waiting here for. We're going to give it some time here. We don't want it to do it immediately. We want to get rid of everything on the screen first, pause for just a second, and then we're going to roll the dying animation of where Miss Pac-Man is rolling around in a circle. So that's what we're doing here. So we're going to wait when we're in that chomp state. We're going to then, after that, set all the ghosts and everything invisible, or don't draw them anymore. And then we're going to put it in a dying state where Miss Pac-Man is going to roll around for a bit. And then here, the entity duration, we're going to reset whatever our current duration is, because, depending on when Miss Pac-Man was chomped, that duration is in some sort of limbo at that point. So we're going to reset it to -1 so it can get a fresh frame of duration. And then we're going to make the frame beyond what it needed to be at that point. That's part of the reset of the framing, or the frames, or the frame animation. Then we're going to play the track of when the player spins around. So we're going to play that chomp track. And then when it comes, when the player is dying, I'll go to this state. So again, we're conditioning on the state. So the next time the update comes on the next frame, we're now in that dying state. And what we're going to do here is going to wait until we get to the 10th frame. And once it gets to the 10th frame, that means that all the frames of the player spinning around happened. Then we're going to set the state to dead. Now the player is done. We went and showed all the states that we needed the state to show. And when the player is finally dead, we're going to have an increment timer again. We're going to wait 40 frames. And then we're going to reset the frame counter, which is the global counter that is run on main. And we're going to set our substate to 9. Substate 9 in the game engine is resetting the stage. So we're going to tell the engine, all right, player's dead, let's reset the stage, and then that'll do all the functionality of resetting the stage. And then this is for everything else. So if none of those states are true, so if the player is not in any of these states, the default state is us just waiting for the player to press a key. So if it's player 1, we're going to check if they press the key right, or key down, or key left, and key up. These are all provided to us from Devkit SMS, another convenience there, where we are keeping the keys held in this global variable, and we're just going to check if they press right, if they press down, or if they press left or up. And what we're going to do based off of those key presses, we're going to call that move player function that we defined all the way up here, and we're going to hand it the direction that the player wanted to try and go into. So that's what we're doing here. So we're going to hand it the current player that did the inputs, and then we're going to put in the direction that they wanted to try to go. So if they're trying to go right, they're going to hit that. If they're trying to go down, left, up, whatever, that's what'll happen. And then if none of that's true, it's just going to move the player in the current direction that was last set for the player. So that's all it does. And that does that for player 1. And then if the index is player 2, then it would do this. I should probably hard code it that it's for player 2, because technically, I mean, if you're on a nah, that won't matter either. I was thinking maybe you could move the entity if it was in a cutscene, but that's all based on state anyway, and we already break out of it. So, whatever. I'm thinking to myself there. So, and this is for player 2, and capturing the inputs there. Again, Devkit SMS, providing some nice functionality for us to be able to capture that and to condition on those. And then the very last thing, and I know this is going to be a lot of code here, so brace yourself. Kidding. So then this is where our update player happens. As I said before, I like to have 2 major methods, one for loading and then one for actually updating on every frame. And this is that. This update player is basically calling all the stuff that we already have applied. Again, it's the whatever player that we're trying to update, so we're going to hand it over. And we're going to update our sprites so we can draw something on screen. We're going to update our player state, which is the thing that we just showed here. And then lastly, we're going to update our player frame durations and our animations here. So, and that's all this does. This is going to call all the work that we already defined, and it's going to put it in one convenient call for the engine. So the engine's going to call this code at some point in time to update the players that are player on the stage, and that's it. And at some point in time, I'll take a look at this. I'm not exactly sure why that's showing up there. I do have PSG lib. I may have screwed around the lib. Let me see if I did. I can't look at that. All right, let me see. Curious, and I don't want to leave things on not looked at here. So hold on one second. So I'm looking for player. So we're gonna grab that. Let me see exactly where is defined quick. It is under that PSG lib h 2. Oh, that's right, I forgot. For some reason it doesn't like when these hashtags are in here. For whatever reason I removed them out of the lib that I originally used. So if I hit save, see if it fixes my problem. It does. All right. Okay. And I think that's everything. There are some things that we define here that are functions that are not in the game yet, and those have to do with the bonuses and the ghosts, because we haven't gone through those sources yet. But those will be the next two sources we go through. We'll get the ghost source code, which is the biggest source code, and then after that we'll get the bonus source code done, and then we'll finally go to the stage source code, where we will actually be running the game engine, loading our resources that we've defined up to this point, and I'll go over loading those resources and running Emulicious and taking a look at some of the stuff that it offers, so we can look at performance and what to look for when you're actually creating your game. So that's everything. Until next time.